as advertised, I'm going to speak today about field patching and algebraic structures. And I'm really grateful again for the opportunity to give this talk. So first off, let me just say, the goal of the talk, broadly speaking, is to discuss arithmetic. And so let me say very briefly what I mean by arithmetic. So very broadly, there's a kind of imaginary dichotomy that I would like to present between what we might call geometry and arithmetic, perhaps a false dichotomy, but still useful sometimes. So by geometry, we might mean the shape of solutions to equations, most often over the complex numbers, and kind of visual, or geometric properties that these solutions might have. But when we talk about arithmetic, we're often interested in whether or not solutions even exist. So in some sense, arithmetic happens when you start failing to get solutions to equations. And of course, there's a beautiful interplay between these two sides, but I just philosophically want to say that we're going to be on the right-hand side of this dichotomy for today. Now, it turns out that in some sense, this arithmetic can be encoded often in the behavior of algebraic structures, very broadly speaking. And so what I mean today by an algebraic structure is simply, I guess I can point with this thing, is simply finite dimensional vector space with some sort of extra structure generally encoded by linear or multilinear operations, things like multiplications, inner products, things like that. So as a kind of testing ground to kind of describe the situation, I'm going to focus on quadratic forms for a while. So just so we're all on the same page, when I say a quadratic form, I simply mean a degree 2 homogeneous polynomial in some number of variables. And the coefficients are going to be in some field k. What we would like to do is first ask the question of if somebody gives you such a quadratic polynomial in some number of variables, can you find some tuple of elements in the field that you might substitute in for these indeterminants and get it to be equal to 0, where not all of your entries should be 0. So just to kind of warm up, let's do an example, right? So let's pick our favorite rational number and consider this 5-variable quadratic form. So just the sum of the first 4 variables squared, and then minus a times the 5th variable squared. So this one, is chosen so that we can kind of work with it very quickly, and because if we notice, we can kind of clear denominators. It's a little messier than I had hoped, but clear denominators and kind of shift. And what we get is that we can rewrite this as the sum of c times these variables squared is equal to ac x5 squared. That was supposed to be squared. Okay. Anyways, so and then you can see that if I set x5, for example, equal to 1, and I think about yi to be cxi, then this looks like the sum of the y squared. I have 4 y's, y1 squared plus y4 squared is equal to ac, and these are all integers, because I've cleared denominators, or the AC is an integer. And so in fact, by Lagrange's 4-square theorem, we can solve this actually in the integers. We can solve for y, we can solve for values of y that are integers, and then dividing out by c, we can solve for the x's and the rational numbers. So this is a particular example of a case where we can find a 5-variable form, and we can show, and it's slightly non-trivial in that we used Lagrange's theorem, that we actually could solve this equation. And so this was a very special form, but it's natural to ask, did it need to be so special? What if you picked an arbitrary degree 2 polynomial in 5 variables over the rational numbers and asked, does it have a 0? Well, okay, so there's kind of a stupid counterexample to this. Not to be too pejorative, but stupid counterexample, which is, what if I just take the sum of the squares of the variables, right? So of course, you can't solve for that being 0 in the rational numbers unless all of them are 0. So this one doesn't have any solutions, but it turns out that's the only problem. So namely, one has the following theorem. So suppose you have a quadratic form, you want to know, does there exist a solution, not all 0? And the answer is that's if and only if you have 5 variables, there's a solution in the real numbers. So in fact, the sign is basically the only problem with finding a 0 to a 5 variable form. And this is sharp in the sense that if there are plenty of 4 variable forms over the rational numbers, which do have real solutions, but don't have rational solutions. All right. So, okay. We can complicate this question a little bit further and thereby get a slightly nicer and simpler looking answer by thinking about other number fields. So that is, what happens if you extend by allowing your coefficients not to be just in Q, but Q adjoin things like the square root of 2, square root of -5, etc. So in this case, basically the same kind of result applies, except we have to be a little bit careful because these things don't come with kind of a natural embedding into the real numbers. So for example, if I think about this field, even though it looks like it's sitting inside the rational numbers, how I constructed it, I could kind of write it more abstractly as adjoining something whose square is 2. And in that case, I can stick this into the real numbers by associating this new thing either with the square root of 2 or with negative the square root of 2. And so in that way, you get kind of 2 different ways that K can be embedded inside of the real numbers. And this thing, of course, you can't embed inside the real numbers at all because, you can't take the square root of a negative number in the real numbers. All right. So in any case, the theorem then, though, with this kind of proviso says that if you have a number field, so K is a number field, and you have a quadratic form still in 5 variables, then it turns out there exists a solution in this number field, if and only if for every way of embedding into the real numbers, there is a solution in the real numbers with respect to that form kind of interpreted as a real form. So again, with 5 variable forms, basically the behavior over the real numbers is the only obstruction. All right. In particular, in the case of an imaginary number field, so something like Q adjoin the square root of -5, the kind of simplest possible thing happens, which is you have 5 variables, there are no real embeddings, you always have a non-trivial 0. So to keep track of this, one often describes this thing called the U invariant of a field. So the U invariant of a field is the maximal number of variables for a quadratic form with no non-trivial zeros. And so for K, an imaginary number field, the U invariant turns out to be exactly 4. So it's easy to write down 4-dimensional forms that don't have zeros, but more than that, this theorem applies and you have to have a 0. All right, and I have no idea why it's called the U invariant. I should have looked. I'm not lost in the sands of time, I guess. All right. Okay. So Okay, so that's kind of part one, but let's kind of move into to part two. Let me ask the following question. So like, you know that if you have your coefficients in an imaginary number field, more than 5 variables, you can always find a solution, but somehow like it would be nice to imagine, this is kind of a naive, hopeful question, that there should be a way to express that solution or some solution in terms of the coefficients. So in some kind of natural, kind of like algebraic way. This is in fact kind of a little bit overly hopeful and naive, but still let's just like ask this question. So for example, let's suppose in what I've written down here, I have, excuse me, I knew this would happen, but let's see, where was I? I was there. Okay, pretend that didn't happen. So, in this example, what I've written down, so here are my variables, these x's, but I also I have my coefficients in some imaginary number field. Maybe here I'm imagining that k is something like q adjoint I, for example. But some of my coefficients have this parameter t in them as well. So the idea is that, you know, if I specify any particular value of t, some element of k, then we know it has a 0. But can we describe like kind of how some solution or a kind of this collection of solutions might kind of vary as I vary t? In other words, can I kind of like write down a solution which behaves in some kind of algebraic way nicely with respect to t? Can I kind of get a parameterized set of solutions to this? So, you know, what are we really asking? You know, we're really looking for some v. This doesn't erase, does it? Maybe this. Okay, it's kind of horrible, but okay. We're kind of looking for some v of t. So some, you know, v1 of t dot 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 v5 of t, where these vi's aren't just in k, but they are functions, rational functions of t. So kind of expressed as ratios of polynomials. We want to kind of be something kind of depending on the field operations. You know, you can take your parameter t and you can add it to things, multiply, subtract, divide. So this kind of naturally wants to, we're looking for some kind of expression in this field for our answer. We can make this problem a little bit more intricate and ask, instead of just having a free parameter t, maybe we can think about, so in the previous example, we had a quadratic form, a kind of family of quadratic forms parameterized by this t. But we might instead ask for our parameter to, for example, range through points on an elliptic curve or something like that. So in this case, we might consider, for example, the solutions to this equation. This is some elliptic curve, which we would draw like that. And if you look at polynomial functions in x and y, where you identify y squared with f of x, then what you're essentially doing is you're describing functions on this elliptic curve. And then I can look at the fraction field of this, which gives me rational functions on this elliptic curve. And then I could ask if I have some quadratic form whose coefficients are functions on my elliptic curve, can I then kind of parameterize these solutions? So you can kind of imagine what's really going on is this quadratic form is some sort of like a, you know, it's like a machine where you kind of like assign at some point p equals xy on the elliptic curve. So some solutions to this equation, and this thing then gives you some actual quadratic form with coefficients in k. So kind of depending on that p. And then what we want to say is, can we find a set of solutions that's also parameterized by this curve? Okay. So, yeah, the answer is no. I mean, I said it's a naive question, but it's, let's see what we can say about it. So it turns out that it's not hard to write down quadratic forms over fields like this, say in 5 variables, and even all the way up to 8 variables with no non-trivial zeros. So it's possible to find such things such that, you know, for every point on the actual curve, when you evaluate it and get a form, there is a solution, but there's no kind of like nicely varying set of solutions to that quadratic form. On the other hand, but for K, an imaginary number field, every Q in 9 variables that anyone has ever written down has had non-trivial solutions. The expectation is that the U invariant of this field should be 8. But so far, we still don't understand how to get a hold of that. In fact, right now, there's no known bound at all. So it's possible that there's, you know, a million variable form that doesn't have any zeros, even though we believe that if you have at least 9 variables, you must have a 0. Okay, so I guess, you know, in some sense, maybe I should make a little bit of an admission here, I guess. You know, it's natural to ask, you know, why should you care about whether or not these quadratic forms have solutions or not, right? I mean, that's a very natural question. And in fact, you know, it's not like, you know, kind of the point of it isn't, in fact, whether or not these quadratic forms have solutions. It's the fact that this question turns out to be kind of interestingly connected to a number of other problems and phenomena that cover quite a bit of ground. So I will get there, but maybe we will start to see a little bit of that as we try to understand how we try to solve these things and what kind of goes wrong. So now, how could you try to approach this problem of like trying to figure out whether or not these forms with indeterminants and things like that have non-trivial zeros? So for inspiration, we're going to look back at the kind of classical approach over number fields, which is this, which is due to Hasse and Minkowski. So the most basic idea that we always see in arithmetic is you start with some equation you're trying to solve in Q, trying to solve quadratic form equals 0. You might clear the denominators and then reduce your coefficients mod p. So you might say, well, you know, if I have a solution, you know, x1 squared plus whatever, x5 squared with some coefficients or whatever equals 0, and I'm trying to solve that. If I have a solution to this equation where the xi's maybe are some, I don't know, I've already used the letter A, I don't know, y1 over z1, these are supposed to be integer solutions now. Then you can kind of multiply through your z's, clear your denominators, you would get an integral solution. You could try to reduce mod p for various primes, see what kind of constraints you might have on these solutions. Yeah, this is a general kind of an approach. And so, okay, well, so first you might check in z mod pz, but you know, that's a little bit coarse. You might also then try, in fact, not just z mod pz, but why not, you know, z mod p squared z. It gives a little bit more information. So, and then of course, why stop there? You might look in Z mod P cubed Z. And if you think about kind of trying to get more and more precise estimates on what your kind of integral solutions are like, what you do is something like this, so you start by saying, well, I know my solution is something plus some multiple of P. Then, okay, well, maybe it's something plus something else times P plus some multiple of P squared, etc. You continue this process further and further. And what this kind of has the flavor of are kind of decimal expansions, if you will, that seem to kind of go the wrong way. So you're getting more and more information about your number, about your kind of hypothetical integer solution as you go down this list of further and further approximations. And so it's useful to just formally, so if you actually had an integer solution, then this process would stop at some point, right? So like, if your solution was B was less than P to the N, then once you get, to this point over here, your process would stop and you wouldn't have to kind of do further approximations. But you can formally let these things continue and look at kind of formal expressions of this sort. These things form a nice ring, which is called the p-adic integers. And if you let yourself get some negative powers of P in addition, you get the p-adic rational numbers. The nice thing about these things is this thing is a field and it contains Q, and it has what you might call, metric or topological. Whoa, what happened? Okay, I guess I was there. It has, was I there? Yeah, I think I was, yeah. This field QP has kind of metric or topological information. We can say whether or not two things are close by saying that they're kind of like reverse decimal expansions agree up to some point. And so there's a notion of closeness here. In fact, there is a wonderful tool for solving equations in fields like this. And basically, it's Newton's method. So if you have a solution that's kind of very close in this sense, then the Newton's method algorithm lets you actually get, so if you have something, let's say if you have some V where Q of V is small, then you use Newton's method on V and you get an actual solution by kind of repeating it over and over and taking a limit. And this is usually called Hensel's lemma. All right, so I can now say that from this perspective, the result of Hasse and Minkowski from 1931 is that if you have a quadratic form in some number of variables, then you have a non-trivial zero in the rational numbers, if and only if you have a non-trivial zero in each of these kind of completed fields QP, where you've allowed yourself these kind of limits of these sequences, as well as in R. Okay. There's a similar process that happens for number fields. So I'm going to write case of V for the kind of analog of the field QP, but there's a similar statement where you would just replace all the QPs by these KVs, etc. Now, you can kind of get where we were before because it turns out that if you have more than 5 variables, it's very easy to check that over the p-adic numbers using this kind of Hensel's lemma idea, there is going to be a solution for each p. And so, in fact, the only thing that gets in the way, as we saw before, is the real numbers, once you have at least 5 variables. Okay, so natural to ask, can this generalize to parameterized forms? So forms where you have an indeterminate. So here we're wondering about what if you start over maybe Q adjoin some, Q in 5 variables, or maybe in 9 variables, or who knows what, or maybe in Q adjoin I and something. Oh, I'm sorry, I should have a parameter, Q with some parameter T, maybe some parameter T in some number of variables. We would like to know, maybe I'll just write in general, if you have something in K of X, adjoin some indeterminates. If you have such a quadratic form, the question is, does this have a 0 in K of X? If it does, for example, in each KV of X. So in other words, you would replace all the Qs with QPs, for example. So this was the strategy that was used by Max Lieblich and Paramala and Suresh in this very nice paper in Mathanalan in 2014. And there were some, there's some subtleties here, but what they found is that contingent on a conjecture of Koyotalan, on existence of rational points. What you get that is that U of K of X is bounded by something. So we don't know that there would be 9 variables or the expected answer, but there would be a bound, well, at least contingent on a conjecture of Koyotalan on rational points. So what is just to say, we still don't know anything, but there is some evidence that this that the strategy might be potentially useful. So this is in the case where K is an imaginary number field. But we could ask more generally. Okay, so we'll be unperturbed by that somewhat defeat and ask now instead, what information should we expect to be preserved when we go from a number field to its completion, or similarly from one of these fields to these completions? And so in the original case, so you might say, like, so to understand how much information might be lost, you might ask, if I have 2 quadratic forms defined over a number field K, and they look the same over each completion, then were they actually the same? If they're the same up to a change of variables whenever you complete, do you lose any information? Were they actually the same originally? And this result of Hasse-Minkowski says, in fact, yes. So from this point of view, it's natural to ask, well, what happens when you look at parametrized forms? So forms, let's say, parameterized by an elliptic curve or something like that. And at this point, there is basically a giant explosion. So what you find is that, so there's this very nice paper, Paramala and Sujatha from Commentary in 1990, and they showed that, in fact, you can have quadratic forms that look the same whenever you complete, kind of parameterized quadratic forms that look the same whenever you complete. But it turns out that there's a finite number, and that finite number is exactly reflecting this classical Tate-Shafarevich group of, for example, in this case, an elliptic curve. So I'm not going to go into detail about what this group is, but this is a very interesting group that comes up a lot in the study of elliptic curves. Conjecturally, this entire group, if I don't look at this too, is finite. That's still a big open question, but we do know that the p torsion for every p is finite, and and so in particular the 2 torsion is finite, and therefore, although you lose information going from here to there in terms of quadratic forms, there is a kind of bound on the amount of information that's lost. Okay, so we'll call that a minor victory for now for this method. And so it's then natural to ask, like, does this even help us? Right. So if somebody gives you a quadratic form, go back. If somebody actually gives you a quadratic form over one of these fields, k of x, okay, so you can say that a lot of its structure is somewhat preserved in this field, but can we even understand quadratic forms over these fields? Was that even a helpful kind of reduction to make? So before, in the original number field case, when we were talking about going from k to kv, we had the benefit of the fact that this had this interesting kind of analytic structure, which allowed us to use Newton's method and Hinsel's lemma, which let us often find solutions. What about if we're looking at kv of x? In fact, in the when I was in grad school, the situation there also seemed relatively hopeless. So it wasn't until the late 90s that anybody had any way of approaching quadratic forms over these fields. So again, the conjecture was that the U invariant of these fields should be bounded, and again by 8, but there were no known bounds until the late 90s. So thanks to some work of Saltman on division algebras, Saltman's work on division algebras, which kind of applied via the Clifford algebra construction of quadratic forms, let one get bounds on the U invariant. So suddenly, when this result came out, there was work of Merkuriev and of Hoffman and Van Heel, and then of Parmalat and Suresh. This is 97, 97, and 98, where they were able to show that if you had a form by the end of it, Parmalat and Suresh's result, if you had a form with more than 10 variables, then you would have a non-trivial zero for these curves over p-adics, function fields over p-adics. The conjecture, though, had been that you would need 8 variables, and that was the most that you could have and not have a zero, and that sharp bound wasn't found out until a little over 10 years later. So this was independently done by David Harbrader, Julia Hartman, and myself, and by Parmalat and Suresh, independently and with kind of very different methods. So the method that we used involved this construction that Harbrader and Hartman had developed a few years prior, called field patching. And what field patching let one do is take advantage of this kind of analytic structure, analytic structure of the KVs to make some analog of kind of local meromorphic functions on this X, and kind of think, and these give you kind of arithmetically simpler fields in which you can find solutions and then extract a solution over the original field from that. A few years later, though, there was an important observation of Koyatulan and Parmalat and Suresh, in the Commentary Helvetica in 2012, which was that our approach although we hadn't noticed it at the time, in fact, could be interpreted as some sort of local global result again. So the picture looks something like this. So this is a picture of a field K of X. So K of X, we have like the X axis and the K axis. We imagine it something like that. And the idea is that you can kind of zoom in on K by specifying one of these primes. So I've kind of imagined like rational primes, and kind of zooming in on 2 means that you're kind of looking at at something like Q2, or zooming in on 3 means you're looking at you're going from Q to Q3. And so the idea then was that you can go on the one hand from K of X to these fields KV of X, but then the observation of Parmala and Suresh was that you can take a further step of finding what I'll write as these little W's, which live on the which now live on this field KV and play a role analogous to the primes on Q, and let you kind of look further at kind of doing a similar kind of expansion, kind of like reverse power series expansion kind of thing, reverse decimal expansion, I mean, at these W's. So these, so there are kind of smaller, finer things that you can look at. So all told, the point is that these fields are much simpler because one can, so these are arithmetically simpler, can use Hinsel's lemma, etc. Whereas these fields historically are much more opaque. So then one can ask, well, okay, now it's like a 2-step process. We go from the K of X to these KV of X's to these KV of X of W's. So we like break it up into strips, and then we break the little strips up into little bits, strips and bits. And so then the question is, how much information is lost in that process? Again, a consequence of the work of myself with Harbader and Hartman, together with, for example, the work of Parmala and Sujatha, is that if you're in an imaginary number field and you do this process of, whoops, excuse me. And you do this process of looking at forms that look like your form over each of these strips and bits on the strip, then this is still a finite set. So there are only finitely many other quadratic forms that will have this property. So on the one hand, part of this finiteness is due to the Tate-Shafarevich group, and part of it is due to some other invariants from my work with Harbader and Hartman. All right, so for the last bit here, I want to say just a few words about what happens beyond quadratic forms. So, quadratic forms are, were kind of used somewhat motivationally, but one can ask related questions for other kinds of algebraic structures, by which I mean, again, just vector space together with some sort of multilinear operations like multiplications and things like that. So it turns out that such things are in some sense classified or controlled by their automorphisms, which form some algebraic groups. They're groups that are described as solutions to some polynomial equations that you can think of as kind of analogs of things like Lie groups. And as specific examples, the quadratic forms are related to the orthogonal group. Those are kind of their symmetries. central simple algebras to the projective general linear group, and other interesting algebraic structures come up as well, like the octonian algebras are connected to the exceptional group G2. Okay. And so one can then ask, for some type of algebraic structure, generally one asks this question kind of depending on a particular symmetry group, does one have a local to global principle for isometry? So for example, or isomorphism. So for example, here is this is supposed to be some general purpose symbol for an algebraic object. It might be a quadratic form, it might be an octonian algebra or some other thing, but defined over a number field. We might ask, how many other isomorphism classes of algebraic objects look like this one over each completion? Kind of how much information about these things is controlled by what these things look like over each, let's say, p-adic field. Oh, whoops. And okay, and that, whoops, jeez. Just looking for my pen. Okay, and the theorem. So the well-known theorem of Borel and Serre from 63 says this is always finite. For more specific assumptions about the structure of your groups, so for example, if G is so-called semi-simple, simply connected, one can actually show, and this is an important result of Parma and of Bayer-Flukiger, that that this is actually that you are locally entirely determined. Okay, so let me then kind of end by asking kind of like, what does one expect to happen for these more general algebraic structures over when you have kind of parameterized families of them? And here I will say that that the conjecture, I guess, because we don't have any evidence against it yet, is that there should also be a finite kind of determinability of these things by what these look like when you look at the bits along the strips. So the conjecture is that these things should be finite, up to a finite error, distinguishable by what these look like over these simpler fields. All right, and I guess that's enough for today, since I'm a little bit over. So let me stop there.